everybody to this mini course. I am Salameh Sedaghat from Zahra Technical University. I'm going to talk about analytical properties and application of orthogonal polynomials and special function. Before I start, I'd like to thank SIMPA for giving me this opportunity and for the grant. I will tell you the outline of each lecture that we are going to learn. First, I'm going to talk about a special function, eta function. Eta function have been introduced by Exaro for the first time for solving the Schrödinger problems. This function are powerful tools for deriving the approximation of function which have trigonometric and hyperbolic variations and have oscillatory terms. So in this section, I'm going to talk about this function. I want to introduce them, and I want to investigate some important properties of this function, such as the derivative of eta functions and the generating function and the generating differential equation of them, because we know we can find a lot of important information about functions from their generating function and from their generating differential equation. Next, I'm going to show you the integral representation and the Laplace transform of eta functions. Next, I'm going to talk about a new set of base function, eta base function. Eta base function have been introduced by using the eta functions. The main property of this function is that they tend to polynomial when the frequency tends to 0. So they are suitable for solving, for obtaining the approximation of high oscillatory functions and polynomial. In this section, I want to talk about this function. I want to introduce eta base function, and then I want to investigate some important property of them, such as the product of two eta functions, or the relationship between eta functions and other functions, such as Bessel functions. And from this property, later I want to use in fractional calculus. Also, in this section, I'm going to obtain some operational matrices of eta base function. By using these operational matrices, we want to develop a new numerical method for solving some differential equations, such as state-dependent and time-dependent delay differential equation, also Fredholm and Volterra integral differential equation. Next, we are going to learn how to obtain the error band of the proposed method. Finally, I'm going to talk about orthogonal polynomials. We know that orthogonal polynomials play an important role in fractional calculus, in spectral method, and approximation theory. So in this section, I want to talk about these polynomials, orthogonal polynomials. I want to give you some important properties of them, and then I want to apply them for solving fractional calculus. So in this section, I should give you some preliminary and important theorem and definition about fractional calculus. Before I start, I should give you some main reference that I follow them for these lectures. The first one is exponential fitting by Exaro and Berger. Eta function have been introduced for the first time by Exaro for solving the Schrödinger problems. So in this book and other papers of Exaro about eta function, you can find a lot of information, a lot of good information. The next one is the least square fit of highly oscillatory function using eta base function. In this reference, you can find some information about eta base function. And another In this reference, we investigate some new properties of eta function and eta base function, and also we develop a new numerical method for solving state-dependent and time-dependent delay differential equation. Also, we estimate the error band. And the last one is a book about orthogonal polynomials, and you can find a lot of good information in this book about orthogonal polynomials. Okay, let's get started with some preliminary and simple definition. The gamma function. The gamma function is defined for all complex number except the non-positive integer as this equation. Gamma of z is equal to integral 0 to infinity e to the minus t times t to the z minus 1 dt. Here, real of z is bigger than 0. By using integration by parts, we can find that gamma of z plus 1 equals to z times gamma of z. And also, it is simple to find gamma of 1. Gamma of 1 is integral 0 to infinity e to the minus t dt, and it can be obtained as 1. Combining equation 2 and equation 3, we find that for a non-positive, for non-negative integer, gamma of n plus 1 is equals to n factorial. So here we don't have complex number. Another definition is about beta function. Beta function can be defined by integral 2. And what's that? Beta of u and v is integral 0 to 1 t to the u minus 1 times 1 minus t to the u minus v minus 1 dt. Here, real of u and real of v, both of them are bigger than 0. There is a connection between gamma function and beta function. And what's that? Beta of u and v is equals to gamma u, gamma v divided by gamma u plus v. For these, real of u and real of v is bigger than 0. Now I want to prove that. Okay, from the definition of gamma function, we can write, we know that gamma of u is for gamma u, and for gamma v, we know that it is so we can write it in this form as a double integral now. We apply change of variable x t equals to xy, s equals to x times 1 minus y. So we can write by a simple calculation x equals to t plus s and y equals to t divided by t plus s. So we can write this integral as e to the minus x t x to the u minus 1 y u minus 1 s okay. The Jacobian of this transformation is determinant of derivative, partial derivative of t to x, partial derivative of 2 and this, and it will be minus x. Okay, and for these double integral and for this changing of variable, we have here minus x dx dy. Here, when t goes from 0 to infinity, x goes from 0 to infinity. And when dt here ds, s goes from 0 to infinity, y goes from to 0. So we can write for x dx dy, yeah, minus 1 dx, and for y we have dy. From the definition, we know that it is gamma of u plus v, and we know that it is beta function, gamma, yeah, درسته, beta of u and v. So we can find that gamma u times gamma v equals to this one. And we can write and it is the relationship between beta function and gamma function. Also, from beta function, we can find some important integrals that they are very useful. And now I want to show them to you. Okay. From the definition, we know that integral 0 to 1 x to the u minus 1, yeah, dx. And it is very easy to show that beta of u and v is equals to beta of v and u. Now, in this section, I want to use the change of variable x equals to cosine 2 phi. So we can write beta of u and v equals to x cosine of 2u minus 2 of phi times 1 minus cosine 2, it will be 2, and dx, it will be when x goes from 0 to 1, phi goes from p half to 0. Okay, so we can write it because of this minus cosine 2u minus 1 of v v minus t phi. And we can use it directly to obtain some integral from 0 to p half, and this product. For example, if we set u equals to v equals to half, we can find from this integral integral 0 to p half cosine 2 half minus 1, it will be 1, similar to this, and we have, and I forget 2 here, 2 times p half, and we know that it is gamma half times gamma half, so we can find it, gamma half is the square root of p. Also, another integral that I want to show you, it is here by changing the variable x equals 2 minus a divided by b minus 1. We can find that equals to integral. We have here t minus a divided by b minus a to the u minus 1. 1 minus, it be b minus t minus 1 and dt. So we can write it u plus v minus 1. And integral goes from when x is 0, t is a, and when x 1 goes to b. Integral a to the b, t minus a, b minus t, dt. So for obtaining this integral, we can use the definition of beta function and we can obtain it directly. Okay, and now I want to show you an important rule. Okay. From the definition of beta function, we know that gamma of u, here we have gamma of v. I want to write it gamma of u divided by gamma of 2u. It will be 0 to 1 dx. Okay, by using the change of variable, we can write it x, yeah, Okay, and we can write it in this form. We know that the integrand here is even, so we can write it here again by changing the variable. We can write so it will be ds. And from the definition of beta function, we know that it is beta of u and half. So we find that gamma of u divided by gamma of u to u is beta of u and half, and we can write it gamma u gamma half, and we know that from here gamma half is okay, we don't have it, is radical is the square root of p divided by gamma u plus half. We can omit from here, and we have gamma of u divided by gamma of 2u is equals to this, and it is famous as legend duplication formula, and we use it a lot in this lecture. Okay. Here I have another definition, hypergeometric function. What's that? Real parameters p1, p2 to p alpha and q1 to q beta. Here qj's are not zero and integer, non-positive integer. We define the generalized hypergeometric function by this symbol f of alpha and beta, and has this series expansion. In this expansion, this symbol is the Pochhammer symbol and can be obtained by this p0 equals to 1. Pk can be obtained by the gamma function, gamma of p plus k divided by gamma p. In this formula, in this equation, if alpha is less than or equals to beta, this series expansion is absolutely convergent for all value of y. If alpha equals to beta plus 1, this series expansion is convergent for absolute value of y less than 1. And for absolute value of y equals to 1, this series is conditionally convergent. And for alpha bigger than beta plus 1, it is divergent. Another definition is Bessel function. Bessel function of first kind, because it has some different kind, can be denoted by j of mu. The Bessel kind, the first kind of Bessel and of order mu of y has this series expansion, and we know that it is converges for all value of y. And the modified Bessel function can be denoted by this symbol I mu of y, has this relationship between modified Bessel function and Bessel function is equals to I to the minus mu, special function of order mu of I y. And here I is the complex unit. It is easy to show that modified Bessel function of first kind is a real function of y. And I want to show you something about Bessel function. Okay, we say that Bessel function of y has this series expansion. Okay, factorial. Okay, we can write this mu here to infinity minus one. And also we can write it and from the Puchhammer symbol we can write and from the definition of hypergeometric function, we know that it's a hypergeometric function of order 0 and y mu plus 1 and four. So we can write the Bessel function of order mu, the first kind, in base of hypergeometric function of order 0 and 1. Also, if in this series expansion we put iy instead y, we can see that we have I to k divided by k factorial. And we can write it I to the 2k here, I to the mu. So we can find that I'm to the minus mu times g mu iy equals I mu I minus mu I mu summation here I forget half. And here it's so we have these three expansion for modified Bessel function. The difference is here. Here we have for gamma function for Bessel function we have that -1, and here we have 1. Okay. Now I want to talk about eta function, a new function, and a special function, eta function. And what's that? Eta functions denoted by eta n of y. Here n is bigger than 0 and are defined in terms of the recurrence relation. Eta n of y is eta n minus 2 of y minus 2 times n minus 1 times eta n minus 1 of y divided by y. Here we have these two definitions for eta minus 1 and eta 0. Eta minus 1 for negative and 0 y can be defined in base of a trigonometric function, cosine of absolute value of y to the half, and for positive y can be defined in base of cosine hyperbolic of y. And eta 0 of y for negative y is in base of sine function. For 0 it is equal to 1, and for positive y it is in base of sine hyperbolic of y. Now I want to show you some properties of this function. Okay, so I told you eta function of y can be defined divided by y. Here eta minus of y we know that we can write a trigonometric and hyperbolic function in base of exponential function. So we can write eta minus 1 of y equals to divided by 2, and then use we can use both of them as eta minus 1. And for 0 we know that it is for negative y, for 0 y it is 1, and for positive y it is also we can write eta of y, eta 0, for y equals to 0 it is 1, and for in base of exponential function divided by 2 square root of y. Okay, these are eta function of order n. And now I want to show you some properties of this function. The first property of eta function that can be obtained easily from the definition of them is that eta n of 0 equals to 1 divided by 2n plus 1 to double factorial. Here, double factorial is I from 1 to n. And there is a relationship between double factorial and 1 factorial and factorial, and it is that. Double factorial is 2n plus 1 factorial divided by 2n times n factorial. Okay. Another properties of eta function is that we can write this series expansion of eta function, and by using the Taylor series of sine and cosine and hyperbolic function, it will be obtained easily. Now I want to show you another series expansion of eta function. So we have okay. Here we can write it gamma k plus n plus 1. And here we can write it gamma plus 2. And by using the Legendre duplication formula, we have gamma k plus n plus 1 divided by gamma 2k plus 2n plus 2 is equal to 1 minus 2k plus n plus 1 square root of p divided by gamma k plus n plus 1 plus half. So we have, by substituting this instead this term, we can find eta n of y okay, and I want to use this. K factorial minus 2k here appear. Okay, so we have another series expansion of eta function we have here. Now, if I divided this term and also this can be omitted by the definition of common symbol, we have it is n plus k. So we can write it half in base of eta function in base of hypergeometric function. Okay, so we have these relation for eta function too. Okay. In this section, I want to talk about the differential properties of eta function by using the definition of eta function. Okay. From the definition of eta function, we know that eta function, we can write it in base of these series expansion. I want to use this. 2 minus n plus 1 square root of p from 0 to infinity k factorial. Now I want to obtain the derivative of eta function. So here we have this term. And this summation is valid for k from 1 to infinity. Now we set q equals to k minus 1. So we can write it two minus n plus 1 square root of p q from 0 to infinity 1. Here we have q plus 1. I want to in this form. Here we can write this. So we have y to the q divided by q factorial for k is q plus 1. I want to use it here and write it as this. Okay, and also I can write it 2 minus n plus 2 times half and this, and it is half times eta of y of order n plus 1. So we have these properties for derivative of eta function. Okay. Another property of eta function is that the generating differential equation of eta function can be obtained as this equation. Now I want to obtain it. Okay. Okay. From the definition of eta function, we have this eta n of y equals to eta n minus 2 of y minus 2n minus divided by y. Here, by putting n plus 2 instead, and we have eta n plus 2 of y times y equals to eta n of y minus 2 n plus 3 eta n plus y. From the derivative of eta function, we find that we can write it equals to 2 eta n plus 1, derivative of eta n plus 1 of y. So from this we have y derivative of eta n plus 1 plus 2n plus 3 divided by 2 eta n plus 1 is equal to half eta n of y. Again, we can write it 2 eta derivative of eta n of y. So we have yd plus 2n plus 3 divided by 2 eta n of d eta n of y equals to n y. If we set eta n equals to z, we have y, the second derivative of z equals plus 2n plus divided by 2, the derivative of z equals to z. And now we find that the differential operates the differential equation of eta function as this equation. Okay. Here we have a relationship between eta function and Bessel function. Eta function of minus x to the x to the 2 can be written as the Bessel function of order 1, the first kind Bessel function, and eta function of x2 can be written as a modified Bessel function. And now I want to use them. We use this formula, this equation in fractional calculus, and it is very important because by using this equation we can find that the fractional Astormio of this function, that they are exact eigenfunction of that. Okay, I want to show it to you. Okay, from the definition of eta function, we can write it here. We have y, we can write k factorial, yeah, and We can write it in this form, 2 minus n plus 1 ka from 0 to infinity gamma ka plus n plus half plus 1 minus 1 to the ka x divided by 2 to 2ka divided by this, and we can write it plus n plus half. So here I should write minus, okay, and here we have the Bessel function of order n plus half of x, and here I have so for eta function in minus x to the 2, we can find that it is can be written as a Bessel function, and for eta function on x2, it is easy like this to obtain. It is a coefficient of the modified Bessel function of order n plus half. Okay. In this section, I want to talk about the generating function of eta function. The generating function of the eta function can be obtained as this equation. Here we have ERF of a square root of t half. What's that? It is an error function and can be defined as this equation. In fact, here we want to know about the function that we write the expansion, the C expansion of it, the coefficient of Tn, what's that? And we want to find this function. Okay. Now I want to show you about the generating function of eta function. Okay, so we say that the generating function of eta function is this function. Where error function of the square root of t half has this series expansion. Okay, here by using the Taylor series of this and by the definition of error function, we can write it as I forget to write this section, y divided by 2t. Okay. It's correct. We are F radical. Okay. Okay. We can write it in this form. I want to write the Taylor series of this section. ERF of this. So we have 2 divided by square root of P e to the minus T summation R from 0 to infinity to R T. Here we have T to R plus 1 divided by 2, and here we have 2R plus 1 double factorial. Okay. We can omit this term. And here we can write, finally, okay, here we have e to the t2. Okay, r from 0 to infinity, t to the r divided by 2r plus 1 double factorial. And by using the definition of 2r double factorial, we can write is factorial divided by r factorial to r. So we have here we have to infinity y k divided by times k factorial, and for that we have t to the r and 2r plus 1 factorial r factorial. Okay, and we can write it to r minus k y k t, and for t we have tr 2t. Okay, t to the r minus 2 r factorial no factorial. Okay, I think I have here we have factorial. Okay, that's okay. Now in this section I want to pick out the coefficient of Tn, because I want to write this series expansion like this series expansion, and I want to know that the coefficient of Tn in this series expansion can be what? So now we want to pick out the coefficient of Tn for a fixed value of R, the coefficient of Tn can be obtained by taking R minus nu equals to n. So we have nu equals R minus n. So for this fixed value of R, the coefficient of Tn is here, I wrote all of them is R, and I write K. It is a mistake by me. Rho is correct. Here is rho because all of that we have rho. 2 to the n R factorial. Okay. To R plus 1 factorial, R minus n factorial. Here is this rho 2. R minus n. Okay. So we want to find the total coefficient of Tn. Here is the total coefficient of Tn can be obtained by summing on all aloft valued of R. So we have the coefficient, the total coefficient of Tn equals to, okay, 2n R factorial y R minus n divided by 2R plus 1 factorial R minus n factorial. Here we know that here nu equals to R minus n is bigger than 0. So we have R is bigger than n. So for this summation we have Rn from n to infinity. We can set Q equals to R minus n. So we have the total coefficient of Tn is Q from 0 to infinity 2 to the n r factorial q plus n factorial divided by 2q plus 2n plus 1 factorial y to the q divided by q factorial. And from the definition, we know that it is eta function of y. So we find that the total coefficient of Tn in the series expansion of this function is eta function. We say that in this part is our generating function of eta function. Okay. Yeah, we have a 10-minute break and then continue. Okay, welcome back. Now I want to show you the integral representation of eta function. Eta function of order n can be represented by the integral of this form. Eta n of y equals to this integral from -infinity to 0, and you can this term here. Now I want to show it to you. Okay, so we have here zero t okay. From this integral, we have by using the Taylor series of this term, we can write from 0 to infinity y divided by 4t divided by k factorial dt. So we can write this to infinity dt y divided by 4 to the k divided by k factorial integral -infinity to 0 e to the t to the minus n minus t divided by 2 minus k. Okay, k. Okay, dt. Now for this integral, I want to use from a Hankel representation of integral. That's it. And it is this integral -infinity to 0 of e to the at t to the minus m minus n1 dt can be obtained as this term. Here we have A equals 1 and m plus 1 equals to n plus k plus half. So we can write this integral as equals to 2pi mm, 2pi divided by gamma n plus k plus half. And we have this summation. So we have infinity y divided by 4 to the k half factorial is factorial 2pi gamma k plus n plus half factorial. So we can write this integral as this summation. If we, by multiplying this term on both sides of this integral and in this summation, we have uh, 2 minus n plus 1 square root of p divided by 2pi. Here we have 2pi summation 1 divided by gamma of k factorial. And we know that it is a eta function of y of order n. So the integral representation of eta function can be obtained by this integral. Okay. Another theorem is about the Laplace transform of eta function. We want to show that the Laplace transform of eta function is expressed by this equation. Here it's the Laplace of eta n, and here we have e of order 1 and n plus 3 divided by 2. Here is E is the Mitage-Leffler function that I show you it. Okay. I want to show that Laplace of eta function can be obtained by this formula. Here, eta E is the Mitage-Leffler Leffler function, and it can be obtained from this series expansion. Okay. By using the definition of Laplace, we can write it and by using the definition, the series expansion of eta function, we can write this integral as times k factorial. Now we can write this integral as d of to infinity integral 0 e to the minus s y, and here we can write k factorial and 4 to the k, and so we have y k dy, and we know that it is the Laplace of y k and can be obtained by k factorial s to the k plus 1. By substituting this in this summation, we have Laplace of eta n of y equals to 2 minus n plus 1 summation divided by s from 0 to infinity. And from the Mittage-Leffler definition, we can write it as divided by 4s. So we can obtain the Laplace of eta function in base of Mittage-Leffler function. Okay. We have a lemma here. The product of two eta-based function, eta n, eta of y of order n times eta m of y can be obtained by these equation. Eta of, you can see that here it can be obtained as hypergeometric function of order 2 and 3. And now in this section, I want to show it to you. Okay. From the definition of eta function, we can write this minus 2 summation from 0 to infinity k factorial. Here, from the Cauchy rules, for multiplying of power series, we can write this as p 2 minus n minus 2 summation from 0 to infinity j from 0 to k gamma j plus n plus t half j gamma k minus j plus m plus t half y divided by 4 to the k factorial. By using the Cauchy rules for multiplying a power series, we can write this product as this term. 1 divided by here, j is from 0 to k. So we know that we have these two. Yeah. By using the property of binomial, we know that we can write here gamma k plus m plus gamma k plus n divided by gamma k plus m minus j factorial gamma k plus n k plus n plus minus k, it will be j plus n plus k minus j factorial. Okay, by using this fact and substituting it instead this, we can write that as for that we can write k from 0 to infinity, j from 0 to k. I want to say that. And you see that we don't have this term here. So we have y divided by 4 divided k factorial. And by using the binomial theorem, we can write it as we have for this I write this term. It is from binomial theorem. Okay, now by using the definition of binomial theorem, we can write it as gamma of k plus n plus and for this we have gamma k plus n plus n plus n plus 2 divided by gamma k plus n plus n okay. Here by summing these two we have here 2k plus n plus n plus 2 2k plus n plus n plus 2. Okay, y divided by 4 k factorial. That by a simple computation we can find these term. It is a hypergeometric function of order 2 and 3. Okay, the next theorem that I want to show you is this theorem. The eta function satisfies the following relations. Eta n of z equals to eta n of 0 plus z times dn of z. Here, dn of z can be obtained from equation that is okay. I want to show it to you. So we want to show that eta n of z can be write as eta n of 0 plus z dn of z, where dn of z equals to eta n of 0 minus 3 double factorial eta I of z. Okay. From the definition of eta function for eta 0, we know that eta 0 of z can be written as e to the square root of z minus 2 times the square root of z for non-zero z, and for 0 we have 1. Okay, for non-zero z we have eta 0 of z divided by 4 e to the square root of z minus divided by the square root of z. And we can write z times eta z to the 2z4 e to minus 2. Okay, and from the definition of eta minus of z, we know that it is e to the square root of z plus e to the minus divided by 2. So we can use it and write this section is equal to 2 eta minus 1. So we have 2 eta minus 1 of z minus 2. From this, we have eta n, eta minus of z equals to 1 plus half v z4. So for n equals to minus 1, these equations 1 and 2 are valid. Now, by induction, I want to show that it is valid for all value of n. So, when I want to show that by induction on n. Okay, suppose that this equation 1 and 2 is valid for n minus 1. So we have eta n minus 1 of z equals to eta n minus 1 of 0 plus z. This is the number 3 equation, and dn minus z is equal to eta n minus 1 of 0 times n plus 1 n 2i minus 3 double factorial eta I of z. Okay, Suppose that these equations are valid for n minus 1, and now I want to show that it is valid for n2. From the definition of eta function, I have eta n of z, eta n minus 2, here we have z, yeah, minus 2n minus 1 divided by z. Okay, here in this equation, by replacing n plus 1, n by n plus 1, we have eta n plus 1 of z equals to eta n minus 1 of z minus 2n plus 1 eta n of z divided by z. And from this equation, I can write eta n of z equals to eta n minus 1 of z, okay, plus minus z eta n plus 1 of z divided by 2n plus 1. Okay, z. Okay, we can write it. I want to write eta n on base of eta n minus 1 and eta n plus 1. Okay, now by substituting equation 3 here in this section, I can write eta n of z equals to eta n minus 1 of 0 plus z the n minus 1 of z minus eta n plus 1 of z divided by 2n plus 1. And we know that eta n of 0 can be written by this form, 2n plus 1. Okay, we know that it is 2n plus 1 double factorial from the definition of, from the properties of eta function, and we can write it in base of eta n minus 1 of 0 in this way. Okay, so here we have eta n minus 1 of 0 divided by 2n plus 1, so we have eta n minus 1 of 0 plus z the n minus 1 of z minus eta n plus 1 of z divided by 2n plus 1. Now, by substituting equation 4 in this equation, in this section, we want to show that it is the theorem is valid for eta n2. So I have here, I want to obtain this fraction. by substituting this in this, I have eta n minus 1 of 0 divided by 2n plus 1, we have eta n of 0. Okay. Minus I from 0 to n 2i double factorial eta I z minus eta n plus 1 of z. Okay, and we know that here 2 2n minus 1 double factorial times eta n minus 1 of 0 equals to 1. So I can write this term as a coefficient of eta function of order n plus 1. And so we proved the theorem. So we can write it is I equals to 0 to n plus 1. And here is the summation and the theorem proof. Okay. Okay, and the last theorem that I want to talk about this session is this theorem. We have this relation for eta function. The m derivative of z to the n eta function of order s of az equals to this term. Here, by using the Laplace formula for the product of f of z times g of z, we know that we can write it as this series. Suppose that here f is z to the n and g is eta function of order s. We know that the derivative of eta function can be obtained from this equation, and we know that the derivative of a polynomial can be obtained by this. By substituting these two terms in this equation, in this Laplace formula, we can obtain this result for our theorem. Okay. I tell you some other things that I want to talk about eta function, and next session I want to talk about eta base structure. Let me know if you have any question or comment. Thank you.